Good morning. Okay, today's lecture, let's continue on AC mode. So, as we know, the AC mode, or steady state AC mode, will be considered as sinusoidal signal. That's what we discussed last lecture. So it will be as cosine signal with phase shifts. So when we draw the sine or cosine, that's an example of a signal. It can be like this. So the sine or the sinusoidal, it can be, that's an example of maybe sine signal or cosine. And we discussed last lecture, it will be bounded between x max and negative x max. Then this waveform, we used to say it as x of t equal to x max cosine omega t plus alpha, something like that. Then now, as an indicator, if we say that, or like in real life, if we want to say what's the voltage, are we going to say it's 169.7 cosine 377t plus maybe 30 degrees? This is sometimes can be inconvenient, is to have this long expression, especially when we do, for example, sometimes some measurements or when we do some analysis. So this kind of the expression is long. So if I ask you, what's the wall outlet voltage? So you will say it's 120 volts. And what is the wall outlet, is AC or DC? We will say it is AC. Okay, how could this be 120 volts without cosine omega t plus alpha? So basically, we can donate this value or like convert this expression by something equivalent to this. Like what? Like average value. So instead of saying like 120 square root of 2 times cosine omega t plus alpha, so this is sometimes long expression. So what we measure using the DMM, something similar to the average value. So let's think about this. So can we calculate the average value of this waveform? What's the average value? Which is the area under the plot. So we have a positive area here. We have a negative area, right? So the average value, positive area and negative area, will cancel each other, right? So what will this mean? The average will be what? 0. So the average value of sinusoidal basically is 0. So actually, I think the average is not a good idea. Okay, how did they get like the average, for example, to use the wall outlet 120 volts, or how we can get something similar to the average value, but the problem is the average is 0. So one of the approaches is we say the problem that causes the average value 0 is this part. Okay? Someone can say, how about take the average value for the half period? I don't think taking the average for the half period is good because we have missing information, because we're taking it for the half period. Okay. How can we, or the concern is, how can we get rid of this negative sign? We can do the square. If we do the square, I'm going to call it square. If we do the square of positive value will be positive, the square of negative will be positive. Is this correct? Okay. Now the average is no longer 0. Is this correct? So we can take the average. Average, or otherwise we'll call it the mean. We will take the mean. We'll take the mean. Okay? Now, is this the value that what I want? Not really. Why? Because this is the mean of the square. I squared the value and I took the mean. So how can I go back to the origin? By taking what? The roots. Is this correct? So let's take the square roots. the roots of the average, or here, root of mean, whatever, like take the roots. Then we will get a value that's non-zero, and it is something equivalent to the average. But this is not 100% the average. It is the first step we did, stick in the square, then we take the mean, then we take the roots. Or, in other words, we will say it is roots, mean, square. You can go up and say from top to the from the bottom to the top. So we will call it as roots, mean, square, or as a shortcut we will call it RMS. RMS. So as a shortcut, then the RMS value is the value that we will get equivalent to the average, but not the average again because the average is 0. And it can be an indication about the value of the AC signal. So of course, the larger RMS, the larger value, the lower RMS, the lower value. Then that's the topic, which is root mean square RMS. That's why we are using RMS, not the average value, because again, we want to find the average, or to find something like the average, but the average is 0, then we use this value, which is called RMS. Sometimes some other textbook, they will call it effective value, okay? Or the DC value of the AC, something like that. So the AC is long waveform, or I mean, long equation, but we can find the like an equivalent by making the RMS. So the RMS, again, we see that there is a square, then there is the mean. So the mean, like by doing the integral, there is a square root. So this is root mean square. Then, in order to calculate the RMS for any signal, we need to apply this general formula. That can be valid for whatever waveform. If you have sinusoidal, square wave, triangular, sawtooth, you need to apply this formula. However, if we have sinusoidal, there is a result that we will use this, which is the RMS will be the maximum value over root 2. So we will use this. Why we will use this, not the integral formula? The integral formula can take a long time, and we don't need to do it every time, because most likely the AC signal are based on sine wave or sinusoidal waveform. So the sinusoidal, sine or cosine, whatever, the RMS will be the max over square root of 2, and that's it. So we will use this results, because every time we will assume the AC as sinusoidal. We will not assume square wave AC or sawtooth or whatever. This will be other parts of our other courses of electrical engineering. But here in fundamentals, or that's what we have actually in real life, all of the signals are based on cosine, so the RMS will be the max over the square root of 2. Then when I have the digital multimeter, the DMM, that I use it to measure the voltages, it will measure the RMS. So when we have the grid voltage as 120 volt, or wall outlet voltage as 120 volts, this is the RMS value. And when I say like it's 240, that what you have in your apartment can be either 120 or 240, those are the RMS values. Okay? Now, let me go back to this question that we solved last lecture, and we said like find Vmax, omega alpha, f, t, and I can add something which is find Vrms. This is like for the previous example. So how to find Vrms? Vrms will be Vmax over square root of 2. We know Vmax 169.7, so 169.7 over square root of 2 equal to 120 volts and RMS. Okay? So again, as a result, we realize that the 120 volts RMS, that what we know, like our residential or our home voltages, it's the RMS value. It's not the max. How to find the max will be, this is the overall expression for your home voltage, like with different angles. So it can be 50 degrees, can be other angles. So 169.7 cosine 377t. while the angle can be different depending on each phase. So that's the overall voltage that goes to your home. Then where did we get the 120 volt? Here it's 169.7, it's not 120 volts. How can we get it? By dividing by square root of 2. 169 volts square root of 2 over square root of 2 equal to 120. Okay? Now let's go for more simplifications, which is something we call it phasor and RMS. So basically, as I mentioned, x of t equals x max cosine omega t plus alpha. And we said that the RMS equals to the max over square root of 2. Now, can we replace x max by the RMS on that expression? Yes, we can, because most likely x max equal to square root of 2 times x RMS. So let's substitute this there. This yields to be square root of 2 times x RMS cosine omega t plus alpha. That's how we get this expression. So we have this expression that we know can be written in two ways, in the RMS forms or in the max forms. And that's just the difference is the square root of 2. Okay? Then, look at this expression. We have I of t equals 10 square root of 2 cosine omega t plus alpha, or 14.14 cosine omega t plus alpha. So basically, this is equivalent to x, or I RMS, times square root of 2. This is equivalent to I max. So whenever you wrote the function as 10 square root of 2, or wrote the function as 14.14, whatever you want. So you can either keep it like 10 times square root of 2 without making the multiplication. That can be fine. It can be correct. Or you can write it as 14.14. Okay? Keep in mind, again, the default value for the currents to be at the RMS, not the max. Whenever you see a system or a device that has this currents, then if there is nothing about it, there is no expression, there is no indication says this is the maximum value, then every time whenever we read anything about like the label on, for example, like any electronic devices or that supports AC, then the currents given is in RMS. Then, so whenever again you write the expression, it can be RMS times square root of 2, or you can do the multiplication. So if we want to plot 14.14 cosine omega t, it can be something like this. Something like this. So the maximum and the minimum between 14.14 and 14.14. While the RMS, like this, at 10 amperes. So this is I RMS, and the other thing which is I of t. Then basically, the RMS says that instead of having this waveform like that, what we have, like when we have this sinusoidal or cosine waveform, we can find the DC equivalents by making it as a straight line as 10 amperes, something like that. So which we make the convergent for it. Then this will make the life easier in doing some analysis in some circuits, so or some as an indication. So the 10 amperes is not actually what's happening in the real life. What's happening in the real life is the cosine waveform, but we replace it by equivalent value so it can be easier to understand. Now, how can we solve the AC circuits? Let's look at this example. We have this small circuit as voltage source, resistor, and inductor. Before we discuss this, or in DC, we used to say, in DC, we used to say L is short circuits. So there was a source, resistor, and short circuits. Then if we need to calculate the currents, I will be V over R. That was in DC. Okay? But in AC, L is no longer short circuits. It's no longer short circuits. So what should I do? It will be kept as is. We cannot eliminate L. So how to solve the currents? Let's do KVL. I'm going to assume here is the current direction already been assumed. And let's do KVL in this loop. And I can assume here as plus minus VR. So KVL in AC, we will do KVL mesh 1. Start from the left bottom corner, then counterclockwise. So it is negative Vs of t plus Vr of t plus VL of t equals to 0. Then substitute. Vs of t is given as negative V peak or V max cosine omega t plus Vr of t, which is for the resistor. You can use Ohm's law, which is I times R. Then it will be as R times I of t. Then plus VL. What's the voltage across the inductor? Anybody knows? Do you remember the inductor formula? VL equal L di by dt. Do you remember this? Yes. So that's what we will substitute. So times L d by dt of I of t equals to 0. Okay. So what shall we do? What do we need to do? Then we can put here L di by dt plus, let me substitute divide by L. So it will be plus R over L I of t, and I'm going to move them to the other side. V max divided by L cosine omega t. Now, this equation, it is first order ordinary differential equation. Okay. How can I solve this? How can I find the currents? Solve this differential equation. And keep in mind that cosine omega t, this will make it more complicated because we have, it's not constant, this part, it's cosine. So there will be completed homogeneous solution, completed solution, then you need to find the overall answer. Then I of t will be, after doing this analysis, will be V max over square root of R squared plus omega L all is square cosine omega t plus tan inverse of L over R, then ampere. So it will be as a time function, but there will be that long. Okay, even though the requirement of this course is to know the differential equation, but I'm not expecting to do this. This is just a simplification, a simple circuit. How about if we have multiple of series and parallel elements? It will take so long, and it requires complicated math. So solving this differential equation is not fun. Okay. How can we solve this differential equation in better way? One of the approaches, we use Laplace transformation, right? If we use Laplace transformation, then we can make it better, so it can be as S, something like that, Si minus I of 0 plus R of L over Li of S plus equal to V max. Then you need to convert the cosine. So something like that. You can use Laplace transformation. I'm going to erase this. So if you use Laplace transformation, you can find the answer. So it can be easier. But the thing which is, even with Laplace transformation, we still have some complicated. Now, our target is to solve these circuits in much easier way, or in faster, as well as in faster time. Therefore, in our analysis in electrical engineering, we created techniques to solve these circuits in much easier way, other than Laplace transformation, other than the time domain. So by basically we will assume this circuit, it's working under a constant frequency. So for example, we know the grid frequency here is 60 hertz. Then whenever we are in the United States, it's 60 hertz, so it's fixed. Then I don't need to worry about the frequency. So I'm going to convert the time domain into frequency domain. So you will go from time domain to frequency domain. And by the way, Laplace transformation is one of the techniques to do the frequency domain. So Laplace transformation is actually in frequency domain. Then we will not stop here. We will use a special tool, or we created our own domain that's called phasor domain. So phasor domain is actually like a domain that we created that can make solving the electrical circuit analysis much easier. Then we don't need to use the differential equation techniques. So phasor domain, something similar to Laplace. So Laplace transformation, we used to like have a table, convert this to this, this to this, this to this, something like that, other than using the integral. But we used to have like a table, then you make this conversion. While here, instead of converting as a math equation, we will convert the electrical elements. So let's convert the voltage source, convert current source, resistor, inductor, capacitor. So that's it. Then we will do our own version of transformation, so we can use this to solve the circuits. And actually, we realize that when we convert the system into phasor domain, the circuits, AC circuit that we know, will be very similar to DC, such that we will have a constant voltage, constant currents. We will have something similar. Then we can apply the DC circuit techniques like parallel, series, etc., so which will make the life easier. Then here in phasor domain, it's actually will be time independent. Then also here we will assume we are at constant frequency, and that's what we have, constant frequency. Okay, how can I convert the voltages or the currents into the phasor domain? Basically, we used to have V of t as V max cosine omega t plus alpha, or in other words, it can be square root of 2 V RMS cosine omega t plus alpha. So do you agree with me on this? There is the formats, time domain, or I'm sorry, in terms of max, in terms of RMS, right? Then, in order to convert this voltage to the phasor domain, it will be as V bar equals to V RMS angle alpha, or if we have the max representation, will be V max divided by square root of 2 angle alpha. Whatever you have. If you have the max representation, divide by square root of 2. If you have the RMS, it will be the RMS alone. Then we realize that this is the overall, this is the RMS value. And alpha are the angles in degrees. The other thing that we see, V bar is complex number. Complex number. So we can realize 3 different things. The first thing is the angle will be in degrees. The magnitude is actually the RMS value. If you have the max, just say the max divided by square root of 2, divided by square root of 2. Then the voltages, it will no longer be function of time, it will be constants. But this constant is actually complex number. So we realize we can convert that time function or time expression to be a complex number. What's the advantage of it? The advantage of the phasor domain, we will no longer see the cosine signal, so it will be constants. So something similar to the DC, you can solve it similar to the DC. The disadvantage is what? It's complex numbers. So the complex numbers means more complicated analysis. That's why we got a lecture before, like 2 lectures ago. We discussed about the complex numbers because we are going to use it here. So again, the RMS will be the complex numbers. So we can do this for voltage and the current. So whenever we have the currents, I bar will be I RMS angle beta, or I max divided by square root of 2 angle beta. Okay? That's how we convert everything. And keep in mind, you must use bar. Bar is a must because it is complex number. Okay? Now, whenever we have any voltage expression, any current expression, we can convert this into the RMS or into phasor domain easy. So phasor to phasor domain. Okay, let's see this example. Convert V of t to the phasor representation. How can we start? So basically, this is equivalent to V max cosine omega t plus alpha. So we will say that's V bar, because in phasor V bar, it is V RMS angle alpha. What's given in the question is the max, not the RMS. So it can be as V max divided by square root of 2 angle alpha. Okay, what's V max? V max is 169.7 divided by square root of 2 angle 50 degrees. Then after simplification will be 120 angle 50 degrees volts. This is V bar. Then this is the answer. This is how I convert the expression, convert this to phasor domain. Now, how about the next one? Try it and tell me the answer. It's your turn. We need to convert this to phasor domain. So the first thing should be I bar. I bar equals to what? I RMS angle beta, right? Or in other words, I max divided by square root of 2 angle beta. Actually, in the analysis, you don't need to over-explain it like this. Just substitute it. You don't need to write here. Just write it just to explain it to you. So in real life, you will say, like when you do the analysis, you will say I bar equals to what? 14.14 divided by square root of 2 angle, what's beta? Negative 30, right? Degrees. So 14 over 14, 14.14 over root of 2, which is 10, angle negative 30 degrees amperes. That's it. Okay? Any question? Now, since, as we know, when we used to do Laplace transformation in differential equation, we used to do Laplace, then we solve the equation, then at the end we will do something we call it Laplace inverse, right? So when we solve the AC circuits, we need to convert the circuit from time domain to phasor domain. Do your analysis. Then when you get your final answer, don't forget to convert it back to time domain, or something called phasor domain inverse. So let's assume we converted the expressions, all of the voltages, all of the currents, to be phasor domain. Then, for example, the question was find the unknown voltage, or find the unknown currents. After doing several analysis, KVL, KCL, Ohm's law, we find the unknown currents. Then we need to convert this back to time domain. How can I convert this back to time domain? Here's an example. After we did the analysis, we have this final answer in phasor domain. The question says find I of t. not I bar. What should I do? Do phasor domain inverse. How can I do it? Basically, in order to solve this, you can know, or as we know, I bar equals to I RMS angle beta, right? How to find the expression? You have I of t expression. I of t equals to I max cosine omega t plus beta. Okay? Then it will be, since we have the RMS, not the max, so we have the other thing which is called I RMS, the RMS formats, times square root of 2 cosine omega t plus beta. Okay? Now, what's the RMS value? Do we know it? Yes, we know it is 15. Do we know beta? Yes, it's 45. What else? The frequency. This is something important, which is most likely I bar will not, the frequency is not mentioned. So what should I choose frequency? You can read the question. So the question here, it says the frequency is 100 hertz, which is given. How about if the frequency is not given? Read the question carefully. It might be given in some indirect way. If there is no information about the frequency, assume the frequency, which is our given frequency, 60 hertz. So I would say if no information at all for the frequency, assume f equals 60 hertz. Assume. Then what will happen to omega? Omega equal to 2 pi times f, which is 2 pi times 60, or in other words 120 pi, or we will say it's 377 radian per second, if there is no information about the frequency. But here, by looking at this question, the frequency is actually given as 100 hertz. So what should I do to find the frequency? We will say that f equal 100 hertz. Therefore, omega equals 2 pi times f. Don't say omega is 100. This is incorrect because omega is 2 pi times f. So multiply by 2 pi. 2 pi times f, which is 2 pi times 100. So the answer will be 200 pi. You can keep it as 200 pi, or you can simplify it. It can be as 628.32. So whatever you want. And of course, the unit is radian per second. Now I'm ready to substitute this in the expression. So I can say I of t equals to I RMS, which is 15, square root of 2, cosine omega 200 pi, plus beta. Beta here is 45 degrees, and the unit is amperes. Don't forget the units. This is the expression. So you can stop here and say like box your final answer. That's correct. And this is the end. You don't need to do other simplifications. If you want to do simplification, also this is still correct if you want to write it the other format, which is say 15 times square root of 2, 21.21. Cosine 200 pi is actually 628.32. I did forget t here. 32 t plus 45 degrees amperes. So if you box this, this is correct. So if you do both answers are correct. You don't need to explain it to the next one, or if you do this, like explain it to the next one, that's correct as well. Okay, any question? Now, the next thing is, now we know how to convert voltage source, current source to phasor domain. Is this correct? We know how to convert V of t I can write as V of t, I of t. V of t, I of t. In phasor domain, it will be V bar, I bar. I have something else, which is, how about if we need to convert other circuit elements? How about if I need to convert resistor, inductor, capacitor? How can we convert this? Okay. So before discussing how we can do this, let's imagine or look at Ohm's law. We know in Ohm's law in DC, V equal in DC, V equals to I times R. In AC, V is complex number. Is this correct? I is complex number, right? What will happen to R? What do you think R will be? Complex number as well. Is this correct? It can be, right? Yes. It can be, or it can, or it cannot. So we can say R bar. But actually, in real life, we don't prefer to use the simple R bar, because R used to be donated for a complex or for a real number. So we will keep the same thing. It will be as I bar, but we will replace it by a symbol called Z. So it will be called Z bar. So Z bar is complex resistor, but again, we prefer the value resistor only for a real parts. We don't prefer to use resistor for a complex number. So we will call it, instead of calling it complex resistor, we will not call it as complex resistor. We will call it as impedance. Okay? It's just like similar in concept, like as a complex resistor, because V equal I times R. V is complex number, I is complex number, therefore Z will be complex number. But we will call it as impedance, such that the impedance is complex number. So what's the impedance? Z bar equals to, since it's complex number, it will have a real and imaginary part. R plus Jx. Okay? This is in rectangular formats. So what's R? R is called resistance, which is the resistor that we know. X is called reactance. Then Z is called impedance. And what's the unit for every element? All of them. The unit in ohms, ohms, ohms. So it's just like we defined like as real part, imaginary parts, then impedance and reactance. Okay? R, Jx. Then we call it impedance, reactance, resistance. Then the next thing, which is, as I mentioned, other circuit elements, resistor, inductor, capacitor, we need to convert them to phasor domain. Or LC to phasor domain. That will be the topic for next lecture. So before ending the lecture, any questions about this? Okay, so let's end the lecture and start